Good afternoon, everybody, and welcome to my talk on directing attention in AR and VR. My name is Anne McNamara, and I'm a professor in the Department of Visualization at Texas A&M University. And I always like to start my talks by telling you guys a little bit about our department, because we're rather unique. We're in the College of Architecture, but half of the faculty are on the technical side, so they have PhDs in computer science. And then the other half of the faculty are MFAs, so they have terminal degrees in fine arts, and they do things like painting and sculpture and all kinds of wonderful things. And then we have the students straddle both sides. So the students are kind of well equipped when they graduate to go work in the entertainment industry, and they go on to work for places like Disney and DreamWorks and Pixar. But recently, students have been recognizing that the skill set that they get at Texas A&M University actually affords them a lot more opportunities, especially in this realm of AR and VR. And we have quite a hive of activity in the AR and VR space at Texas A&M University. I'm not the only professor that's, actively researching in this area. So actually, a lot of my graduate students are here. They're all on this side of the room, so it's kind of funny. But these guys are the ones doing most of the work right now. I took over as graduate program coordinator a year ago, and that's seriously eaten into my research time. So I really am grateful to my team for kind of keeping this research going. So as we all know, AR and VR hold great promise to transform the ways that we work, rest, and play. We also know that a great many challenges lie ahead of us to make these systems comfortable to use and effective to use and also efficient. So in my research, we have two goals, and we kind of look at both AR and VR, and we kind of go between the two. And those two goals are to improve view management, and I'm going to talk about how we do that first. And then I'm going to talk about how we can use some subtle tricks to aid scene navigation or to focus user attention in VR. So for view management, well, we all know that managing clutter in our environment is an important feature. If we want to be able to efficiently search an environment or perform any task in an environment, we all know that clutter is a huge obstacle to this. And even in our 2D virtual world, so in our desktop, and I actually have a colleague whose desktop routinely looks like this, and I have no idea how he finds anything on his desktop, but it's quite comical. And it just really, behooves you that we really need some organization and some kind of better visuals in order to, make our systems more efficient. If we look at augmented reality, if we reveal every possible piece of information about an augmented piece or every virtual label that's available in a scene, well, those labels can quickly overwhelm the user. The screen space becomes too complex. The labels overlap not only each other, but they occlude the real or virtual object that the user is interacting with. And it becomes a fundamental problem in AR. Now, that's not to say that there are many algorithms and strategies that have been proposed to manage visual clutter. So, for example, we can go from here to saying, I really just want to look at the windows. Can you show me the layer of information that just has information about the windows? Yet still we get a lot of information in the scene. And here there's no overlapping elements. I mean, we're seeing a 2D face of the building, so it's quite easy for us to ensure that the elements are visible and understood. What's interesting is that these obstacles can be actually, amplified when we go to a smaller screen. So if we, instead of looking through some kind of a big lens, such as an iPad or whatever, when we go to mobile devices, such as a phone, or even when we eventually go to wearable lenses that are able to augment reality, then this problem is exacerbated. So we're not only going to cover up the labels that we want to see, we're also going to include the real world that we are trying to learn more about. And as I said, many strategies have been proposed to try to alleviate this problem and try to bundle pieces of information into certain pockets. So this is an example from CHI last year, where they used georeferencing to allow people to navigate through the labels in a scene. None of these strategies take into account eye tracking. And our next speaker is from Toby, so I'm interested to hear what they have to say. I don't know if they're here in the audience, but I'm interested to hear what they have to say, because we recently just acquired a couple of eye trackers. But the idea is that rather than display all the available information in the scene, what we can do is figure out where the user is looking in the scene and figure out if there's virtual information available about the object that they're looking at, and then only reveal that information. So rather than show all the virtual labels, we only show the virtual labels where the user is looking. And what's nice about this approach is that we don't need to be exact. We don't need to know the exact pixel that the user is looking at. We can just know the object, so we can know the group of pixels that the user is looking at and then reveal that. So we started out, and this research is supported by the National Science Foundation, and the grant wasn't funded the first time around, and I called the program manager, and he said, well, you're trying to get into this too quickly. He said, so you need to start out smaller. So we started out in 2D. And what we did was we took a range of kind of everyday scenarios that might be amenable to AR. So we had like a cereal aisle, we had a fruit market, we had a used car lot, and just different scenarios that you might find yourself using AR in. So if we didn't use eye tracking and we showed all the available labels, you can see here that the screen quickly becomes cluttered. And this is just with 3 pieces of information. So we tried to be fair in our evaluation. We just used 3 pieces of information. But you can imagine if there was more information about this, if this was a piece of machinery that had an in-depth instructions, that you would quickly see how the virtual labels would cover up the screen space. When we used eye tracking and we asked people to search for things like how much did the honeycombs cost, then you can see that only the label pertaining to the honeycombs is displayed, and then the rest of the scene is visible. So you can quickly then go and see how much the raisin bran is or any of the other of the objects without the screen being overwhelmed with all the labels. So we were looking at different strategies to transition the labels, and we came up with 5 different strategies. And we wanted to see how best to organize these labels based on where the viewer is looking. So we looked at 5 methods that were based on proximity to the gaze point of the user. And all are a function of the distance from the eye to the object. So the first method is naive. It just ignores the eye tracking. The second method, the direct proportional method we called it, or M2, it uses the clamped squared relationship between the distance of the eye and the distance of the object of interest. Method 3 we call spatial hysteresis. And we had a small trigger radius and a larger exit radius. So if your eye was the distance from the eye point is less than the trigger radius, we would reveal the label. And then if it was, as it transitioned out of that larger radius, we increased the transparency and had it gracefully degrade. We did the same thing for time in method 4. So guaranteed that the label was visible for a certain amount of time, and as the eye moved away from the label, it slowly disappeared. So while the timer was running, the information was available, and then it switched off. And then we combined method 3 and method 4 into method 5 with a smaller radius and a larger exit radius, but also made sure that the label was persistent for a certain amount of time. So we took images like the cereal aisle that I just showed you, and we used eye tracking to ask people questions about objects in those scenes. And basically I think we had about 30 participants, and each of them went into one of these groups. And there was 2 conditions. We did it on an LCD size screen, but we also did it on an iPad size screen. And then we looked at the time to respond and how correct people were, so the accuracy when they were doing the search task. And what we found was that the method 3 which presents based on gaze, performed slightly better in terms of the average time to respond rather than the others. The naive method also responded well, but we figured out afterwards that we didn't really use complex scenes. We used scenes where when all the information was available, the labels didn't really overlap and the objects didn't really overlap. So this was kind of like our first study. And we also recognized that the number of errors was lower. Now, when we looked at the tablet-sized screen, we only compared the naive method against the gaze, method 3 gaze method, because we found that had worked best on the desktop. So we found that there was more of number of errors, but at the same time, more of the actual real scene was covered. So in our current user study, what we've done is we would love to move this into AR. We would love to move this whole study into augmented reality, but it's quite challenging to get participants to visit a grocery store, wear eye tracking, walk along with an iPad and perform these studies, and then have them go to a parking lot and go through that, and then have them go to a plant center, a garden center, and do that. So we came up with the idea that we would run these studies in VR, and that's kind of what we've been working on recently. And we haven't actually run the experiments yet. We're just setting up the environments, but we set up similar environments. So we set up like a fruit market, a parking, or a used car lot, a garden center, a library, and some other just everyday scenes where we feel like search tasks would be important. So here we have an example of the fruit market, and the red spiral that you see in the center is actually the gaze pattern. And when the user is doing this, they don't see that red circle; they just see the label. And here's an example from the garden center scene. And again, they won't see that red dot, they'll just see the label. So maybe I'll show you a quick video of that. So let's see. So here you can see the red label the red circle is the eye pattern, and then as they look at the objects, the labels are revealed or disappear. And again, we're about to run a whole bunch of experiments with participants to see which of these methods is more effective. So you can see that it's kind of persistent even as they go away from it. But when they look at the object or in the vicinity of the object, the label is triggered and appears. Okay. So that's just another screenshot. So eventually what we'd like to do is take that out of VR where we have it now. So we have the VR, the HTC Vive is equipped with 2 lenses from Pupil Labs. They're a company in Germany. So that's how we can perform the eye tracking in VR. And then what we hope to do next is once we kind of have a good feel for how that works in VR, we're going to transport those experiments into the real world. And we just, like as I mentioned, we just acquired some wearable Tobii eye tracking glasses, and we'll plan to use ARKit to develop some AR labels so we can get eye tracking in the real world. So that's kind of where we are with looking at visual clutter. And then the second thing we can do is, because we have the opportunity in AR to capitalize on influencing the user's gaze and influencing attention, we can do things in the real scene through the lens that we couldn't do otherwise. And one of the reasons that this project came to light was, as I mentioned before, we're in a department where we have artists and computer scientists. And I was having a conversation with one of the art historians, and he was talking about visual literacy. Is anyone familiar with this painting? Yeah. Okay. So this is the called Tribute Money. And basically, I'm going to go over here, even though I shouldn't, but he's left the room, so I'll just talk loud. So basically, the story of this painting is to be read in a certain way. And when this painting was first painted, people who lived in that time understood how to read the painting. So for example, you start here in the middle, and here's the tax collector, and he's speaking to Jesus, and he's telling him, you owe me some money. Jesus tells Peter, here, to go put his hand in the river and pull a coin out of the mouth of a fish. So then if we go over here, we see Peter in the same clothing that he is in here, putting his hand in the river, taking the coin out of the mouth of the fish. To finish off the story, we go all the way over here, and we notice Peter, again, in the same clothing, handing the tax collector in the same clothing the money. Okay, and that's the end of the story. So how they do this now in art education is they put big red boxes around each kind of area of the screen, and then they show them. So actually, this is just a kind of fast way of enlarging the story. So basically, how they do that now is they put big red boxes around the scene, and they put text on the scene. So it kind of really disengages the viewer from the painting, and it also occludes parts of the painting. So we had done earlier work on something called subtle gaze direction. And this was again using eye tracking. And we leveraged the fact that our eyes are more attuned to motion in our peripheral vision. So sometimes you think that you see a bug in the corner of your eye and then you go to look for it and it's gone. Well, we applied the same idea to images. So say that this is where I want the user to look. This is my area of interest, and the user is fixating down here in this area. Well, if I do some subtle modulation in the peripheral vision, I'll attract the attention. And by repeatedly doing this, I can guide the viewer's gaze around an image. So, and it's just really some simple math. We actually switched off the modulation as the user started traveling toward that area of interest. And we could do that because we were eye tracking them. And essentially during the fast eye movements or saccades, we're essentially blind. So people didn't really notice when we turned it off. We just did some geometry to switch it off. But here's an example to illustrate how gaze direction works. So we as humans are attuned to looking at faces. And so we showed people images without any manipulation, and then we showed a different group of people images with manipulations at certain areas. So this is one of the images from our data set, and we had 20, so we really showed that it did work. So this would be fixation time, and fixations indicate the area of interest. So the redder something is, the more people looked at that area. And that's kind of what we'd expect from this picture, because people are looking at the guide that everyone's holding up, and people are looking at faces. So there's nothing magic there. This shows fixation time where we imposed modulations. So those white crosses are the areas where we put modulations to see if we could draw gaze to those areas. So just by doing subtle modulations in the peripheral vision, we could do that. And here's just a little side by side, so you can see that the difference between the gaze pattern between the two images and that it really worked. Well, then that got us thinking, rather than put those big red boxes around the painting, why can't we do something to the image that would draw your attention? So we tried a whole range of different manipulations, such as burn and dodge and none. And you can even see here where we make things brighter, it kind of attracts the attention. So the idea is you'd be holding your iPad up before this picture, and we could do some modulation on the image, like ideally with eye tracking, but we could do some modulation on the image, draw your gaze around the image, and help, to guide the visual literacy through the image. So these are just eye tracking heat maps, again, from the different regions. And this is with none, so people kind of look all around the image. Here's with dodge, where we emphasize the areas. Here's with a Gaussian blur on the areas that weren't important. And you can see that even anything that we do, so even if we change the contrast, all of those kind of led you around the image in a better way. So then we thought, well, how can we apply that to VR? So I have a master's student working with me now who's actually sick today, so he couldn't be here, Mason Smith. But his idea was to take eye tracking into VR, and then when you're looking at the area of interest, the saturation is fine. But as you move away from the area of interest, he applied this really ugly green filter to the scene, so that when you just become uncomfortable looking at this green image. And as you look back towards your area of interest, then the saturation becomes normal again. So he's actually run some experiments on this. This should be a video. And we might want to go towards the middle of it. But the area of interest here is supposed to be this, the phone box. So as we go away from it, things get darker and greener and just more uncomfortable. And he actually ran pilot studies to see what kind of filters would make people more uncomfortable. So as we go back, then it becomes back to the correct saturation. So as we know, storytelling in VR is challenging because people can look anywhere. So this is just one example of how we are trying to direct the gaze and make sure that people look where we want them to look and hit the story points. And this is an example of the head rotations from where people went away from the area of interest and kind of came back. So this is time across here. And this is the angle difference from where they should be looking. So what we like to see is that people went away but quickly came back. So they went away and came back, away and came back, away and came back. And this pattern has been repeated for multiple scenarios in his image. So in conclusion, what we're trying to do is harness the power of AR and VR coupled with eye tracking to provide tailored, comfortable, and effective experiences for the user. So it's really important as this technology gets pushed out that people don't feel sick and people don't feel overwhelmed by the amount of information and people know what they're supposed to be looking at because, there's no director, there's no direction for you. You actually can look wherever you want. We're really just getting started on this work, so I'd really value your feedback. And when I first wrote this grant 5 years ago, I had no idea how I was going to achieve the eye tracking coupled with the VR headsets and the AR headsets. And I talked about in my grant how I was going to build these things and stick them on in front of an iPad. And now it's just all kind of ingrained and we can buy these things. So I believe that hardware advances will really help us realize the full potential of attention-based AR and VR. And we're really excited to see where this goes. Just to conclude, I need to have some acknowledgements. My students, if they would stand up for a moment. So we have Annie Suther, David O, Ryan Sharp, Catherine Boyd, and Mason Smith is not here. But these four are the ones that are doing most of the hard work at the moment. I just kind of go in and give them a little task every couple of days, and then magically it appears completed for me. Thanks, guys. And thanks to ITC for inviting me down to come talk. We're about 2 hours north of here. We're supported by the National Science Foundation, and thank you for coming to my talk and for your attention. And I would love to have any feedback or questions. I think we have plenty of time. Thank you.